Okay. Good morning, everyone. So last week, we are talking about how to use wave equation to understand the carrier transport in a piece of a semiconductor material. So we have been described some of the cases. The other 4 cases we will discuss. So last week we mainly discussed the first case, which will be the electron in the free space. Okay, so in the case of electron in free space, so we consider the carrier. In this case, we consider the electrons. Electrons travel in the free space, and we consider the free space, so that means we consider the potential barriers equal to 0. So therefore, we can first starting from the time-independent wave equation, and then we start to have this solution, and then we also can consider the equation in here, and then in the end we have the wave equation where it can be expressed as following. I think from this equation is clearly to understand that the wave can be travel in the positive x direction and also the negative x direction. So that's exactly to fit what we expect here, that if you have the electron in free space, there's only 2 possibilities. You either travel to the right or either travel to the left. So now we have the our physics-based speculation can be proved by consider the wave equation. So now we'll move to the second case. So in the second case, we consider there's infinite potential well here. So we still consider region 1, region 2, and region 3. And the main difference is that in the case of a region 1, we have the infinite potential well. And region 3, we also have infinite potential well. So the particle is assumed to exist only in region 2. So that's a consideration in here, assumption in the second case with infinite potential well. And in the region 2, we also expect our potential barrier here is equal to 0. So that's the case of region 2. So with this consideration, first, still we use our wave equation. Now we consider in the region 2 where our potential barrier is equal to 0. So that means in this case, Vx is equal to 0. So again, we can simplify this equation become in here. And one of the particular form of this solution can be expressed by this one. And also now we have to take into account the boundary condition, where the boundary condition should be the phi at x equal to 0 and the phi x equal to a should both equal to 0 in this case, because the boundary condition, the phi in these 2 places should be equal to 0. That's our boundary condition. So once we consider the boundary condition, we can solve this equation where we will get the phi x equal to a equal to 0, which is also equal to the a2 sine ka here. And therefore, we can try to solve this equation, and then we can get the expression for the phi x will be shown here, and which based on this equation we can understand this is an equation to suggest that we have the standing wave So that's also the very the equations are very often seen when we try to solve the standing wave issue. So usually we will get a very similar equation here. So that means that in the case with a particle in the region 2 actually will exhibit the standing wave characteristic. So therefore, we can further consider the equation assuming here, where k is equal. This is based on the property of a standing wave, where our wave numbers can be expressed by the n times pi over a here, and also our wave k can be also expressed by this equation as well, and therefore we can start to have the energy that can be expressed by the different, with considering the different n. So the n is a discrete number, so that means this equation tells us that we start to have the quantization of energy. So this quantization of energy is pretty important. In the end, we can find out that the energy is a discrete number, which has a E1, for example. If we put N is equal to E, then we can have the one energy level called the E1, which is equal to so that's our one energy level. And we can also put a 2 here. So that means we have another discrete energy level. So this is very important. So finally, we start to understand the once we in the very particular case, especially in the infinite potential well, the particle stay in the region 2 will exhibit as a standing wave property. And with considering the standing wave property, finally we can quantize our energy. So the quantization of energy means that the energy of particle is quantized, so can be counted as a discrete number. And therefore, the energy of particle can only have the particular discrete value. So that's a key why that once we consider the electron holes, once in the certain barrier inside, we can always use a discrete energy level to express the property of these electron holes. And then the concepts mainly come from here, where we start to prove that there's a quantization of energy. So now we move to the third case. So in the third case here, we consider the state potential function. So in here we consider there's a state potential function and there's a incident particle try to move towards this potential barrier. So there is a flux of particles incident on the potential barrier. So which means that now there's for example, a carrier try to move to the right and therefore we can divide this with two region. One is a region 1, which is very similar to our free space, and then the region 2, there's a finite potential barrier with potential of V0 here. So now we have to first try to solve the wave equation in the region 1, where we have already this wave equation, and then we put the potential is equal to 0 at the region 1. Then we can start to simplify the equation as shown here. And by considering this equation, we can also get the solution from this equation is shown here, the phi 1x, the wave equation in the region 1 is equal to a1 exponential jk1x plus b1 exponential minus jk1x. So what does this equation mean? This equation means that we have a traveling wave that travel in the two different directions. So the A here, it means that we have the traveling wave in the positive x direction. So that's our incident wave. And the second term, which we found out that there's a traveling wave in the minus x direction. So I think from the physics-based sense, we can already guess that if you have the one incident wave in the free space, and this incident wave will face a certain barrier here for sure. In the region 1, there's only two possibilities of this particle can be traveling. One is to the right, and of course, another one is reflection. So that's actually this expectation, physics-based expectation, now is being proved by using the wave equation. So what I want to illustrate again that why we always have to use a very complicated wave equation or complicated mathematical equation. Actually, the purpose is not to confuse us. It's try to prove our speculation. Even nowadays, if you don't really understand this wave equation very well, you just simply consider the case here. I think it's also very straightforward that once you have an electron moving in the region 1 and try to inject it in the region 2, there's only two possibilities that can happen. One is your particle will move to the right, and also the particle can be moved to the left as well. But now we get more confidence on our speculation, because now we have very solid equation to prove it. So by consider this one in region 1, we can understand there is a wave to the right and then the wave to the left as well. Of course, since in the case of the state function, we are not only considering region 1, but we also have to consider the region 2 as well. So in the case of region 2, we have the potential V equal to V0, which is here. V is equal to V0 in the region 2. And the calculation is almost the same. We're always starting from the time-independent wave equation. But now we have to try to figure out how to address the potential here. But we make a small assumption where our energy is smaller than our V0. I think this is quite makes sense. We consider the case if the energy is larger than the barrier, for sure, the particle can already across this barrier and reach to the other side. But what actually here we want to consider is most of the case that our energy is always smaller than our potential barrier, which is more realistic in our semiconductor device here. So we consider this assumption. Now we can have this equation, and also we consider this equation, we can have the wave, the solution for this wave equation, where can be expressed by this one. But however, the wave function phi 2x must remain finite, because it cannot be increased to the infinite, because the wave and particle here must be finite, not infinite. So that means the coefficient of a B2 must be equal to 0, right? Because if B2 is not 0, and then it doesn't make sense, because of this equation. This is a B2 exponential positive K2x. So if this is B2 is not equal to 0, and this term actually will approach to the infinite, which doesn't make sense. So the B2 must be 0. So once the B2 is equal to 0, now we also back to the very simplified case, which is this one. So now the wave function in the region 2, which is equal to A2 exponential minus K2x here. This is a region where we consider for the region 2. So again, this is another example that although the Schrödinger's wave equation in the beginning is very complicated, but what we are doing is we always try to consider the several assumptions and to make it simplify as possible we can, and then in the end the equation is always looks very simple. This equation is very simple that sometimes you probably just need the mathematics skill that you need in your fresh year. Sometimes even for high school, you already know how to address this the mathematics questions. Okay, so again, we need to still try to solve these phi 1 and phi 2. So now we have a two wave equation here. This is a 1 in the case where x smaller in the region 1, and this is a case in the region 2 here. So just like what we have done before, we try to put our boundary condition to solve the A1 and A2. So the wave function at x equal to 0 must be continuous. So that's a basic I think this is basic rule that the wave equation should be continuous everywhere. So that means phi 1 at x equal to 0 should be equal to phi 2 at x equal to 0. And also, since the potential function is everywhere finite, so that means the first derivative of the wave function must also be continuous, and therefore the derivative of this wave equation at x equal to 0 should be also the same. So we consider these two boundary conditions, we can easily to solve this coefficient where we can get a B1 and A1 and then A2 and A1, the correlation between the B1, A1 and A2 as well. So finally, once we finally can solve the first, we get a wave equation in the region 1, we get a wave equation in region 2, and then we get the coefficient for A1 and B1. And then the last part, which is our conclusion, is that we can understand that in the considering with state function, first of all, we have the flux of incident particles. I think that's a pretty straightforward. We try to inject the particle to the right, and of course we can expect that there's a reflections, right? So we should have the reflection particle as well. So we should have a reflection here. And then we can, this is a reflection. This is pretty fitting for our conventional Newton physics. As I say, that the only minus difference between the Newton and then the quantum physics is just the matter of the tunneling, but the rest of the things are very similar. So in the Newton physics, we also have the concept of reflection. So in the quantum physics, we also have the concept of reflection. So now we can have the reflection coefficient can be calculated by here. So in the case with a region with a state potential, we can consider that the incident and reflect velocity are equal. So then in region 1, we can have this result as shown here. The result of R equal to 1 implies that all of the particle incident on the potential barrier for E smaller than V0 are eventually all reflected. So that means in the end, in these cases with a state potential, once our energy is smaller than the barrier, you have the, for example, if you have a 5 electron try to inject to the right, you will get a 5 electron, all reflections here. So this is very consistent with our classical physics, right? So you throw the ball, 5 balls to the wall, you get a 5 balls rebounds by the wall. So that's ideally exactly the same that when we try to consider the electron movement in the crystal, and then the electron is facing a potential barrier. So this is very consistent with our conventional Newton physics here. So this is also the example that actually the quantum mechanics is not that difficult as you expect. Most of the time, why you feel the quantum mechanisms are way too complicated is because of normally the most of the lecture for the quantum mechanics, they spend huge amount of time to solve the very complicated equation, and sometimes during the try to solve this complicated equation, we are easy to lose to understand the physics meaning behind. So that's why sometimes we feel the quantum mechanics are very complicated. But I believe that so far the quantum mechanics we are talking here are pretty straightforward, are easily understood, and lots of cases you can already expect result, and lots of cases are very consistent with classical physics. Okay, and also in the case of a region 2, we can also have this as we already expressed that this is a wave function for the region 2. So for the case of energy smaller than V0, the coefficient A2 is not 0. So if the coefficient, if A2 is not 0, that means the probability density function, which we have already shown, this is probability density function of a particle, can be found in region 2 is not equal to 0. So that's very important. So the idea is that as we already know that by consider the uncertainty principle and then what we have been described, that we cannot precisely determine the particle. what we can do is only to understand the probability of a particle in the one region. So that's why we use a probability density function here. But very surprised that with considering the region 2, actually the probability to find the carriers, to find the electrons in the region 2 is not equal to 0. So that means we can have a certain probability to find the particle, no matter for electron or holes, in the region 2. So that's the key point. This is the main difference compared to the classical physics. In the case of a classical physics, you know you will not be able to find any carriers or one objective in the region 2 because everything will be completely rebounds. But in the consider the quantum physics, is indeed there is a probability to find the carrier, to find the electron in the region 2. So the results imply that there's a finite probability that the incident particle will penetrate the potential barrier and exist in the region 2. So that's actually why we have to learn the quantum mechanics, why that the conventional physics cannot help us, because of conventional physics cannot understand why there's a chance to find the one, can find something in the region 2. So that's why we need to use a quantum mechanics here. So that means the probability of particle penetrating the potential barrier, that's the difference between the classical and quantum mechanics. So this is the main difference. That the rest of the are very similar. The only and major difference is that even you have the barrier, you have a certain wall layer, the particle still can penetrate. And this is very important for when we try to use this concept to our semiconductor device. Because if you look the typical MOSFET, so I believe so far everyone should be very familiar with what's the structure of MOSFET and the basic operation for MOSFET. So we all know the MOSFET is look like here, which has a dielectric, and on top of dielectric, we have the gate. So we all know that the typical operation for MOSFET is that we must apply the bias on the gate side. In here, we consider to apply the positive gate bias. And once this bias is larger enough, then we can start to induce the electrons. Right? So that's why we talk about the threshold voltage. We talk about how the drain current can flow. But in the previous discussion, we mainly talk about how the electron can be flowed to the right and become our drain current, become our output current. But actually, by consider the quantum mechanics, you apply the positive gate bias here. You have the barrier. Insulator is considered as a wall, is considered as a potential barrier. So actually, your particles in the channel is trying to have an incident to the top, right? So this is exactly the case what we are talking at here. So that's why we have to spend the time to talk about state function, state potential function. Why we have to take the time to explain this case, because this case is in reality will happen. We apply the positive gate bias. So that means we have the incertain particle, which are the full of electron. We'll try to inject it to our dielectric, which can be considered as another state potential barrier. And based on the wave equation, and based on what we discussed here with the quantum mechanics, we can expect, although this is insulator, but actually the electrons can exist in the barrier. In this case, it's a dielectric. So the dielectric should be the insulator. So ideally, you should not be able to find any electrons inside. But now, with quantum mechanics help, finally we can expect that the electron can be incident to this barrier, to incident to this dielectric, and then the electron can be possibly exist there. Just matter with the probability. The probability probably very low, but still, the probability never goes to zero. You will never have the zero probability. It always has a probability layer that the electron can exist in the dielectric. So that's why we have to talk about the quantum mechanics in the beginning, because this is going to help us to understand how the electron and holes transport in our semiconductor. Sometimes not only for semiconductor, because the dielectric insulator, this is not semiconductor, this is pure insulator, but that will help us to understand that why the carriers can travel inside in the insulator as well. Okay, so let's move to the last case. So last case, which we consider that there's a potential barrier. It's basically a combination of all previous three cases, but now we consider that there is a potential barrier only in the region of x equal to 0 and x equal to a. And we also consider that there is incident particles try to move to the right. So now we are going to try to solve the wave equation for region 1, 2, 3 as well. So this is try to solve the time-independent wave equation in each three regions. So as usual, this is what we already have from previous example. We already get the wave equation in all these three regions, which is phi 1, phi 2, phi 3. And now we have to define there's one interesting coefficient. That's where we consider the transmission coefficient here. So since the potential V is equal to 0 in region 1 and region 3, so the incident and transmit velocity are equal. And also we consider the special case where our energy is much smaller than V0 here. Then we can have this equation derived. This is a transmission coefficient. That means that there is a finite probability there's a finite probability that the particle impinging a potential barrier and then will penetrate the barrier and also appears in the region 3. So that's a conclusion. That's we call this as a tunneling effect. So that means you have the, for example, here you have the the 8 particle will try to travel to the right, and suddenly we found that there's a certain particle is being able to penetrate and reach to the region 3, and probably we can find the 2 particles here, and this phenomenon is what we call the tunneling. This is also another difference compared with quantum mechanics versus the conventional Newton physics, because in the case with classical physics, we never have the concept like the tunneling. But in the case with quantum mechanics, so we have the concept of tunneling, that where although you have a barrier height here, but in the end, you still can find the particle in the region 3 as well. Even your energy is much smaller than V0. So this is in the case, even your energy is small, you can possible to have the particles here. And this is just a last reminder that actually we can also extend what we have been done to the 3 dimension. So in the case with 3 dimension, we can consider the spherical coordinates here. And here we won't go very detailed, just try to use the spherical coordination to express in the wave equation. In the end, we can have this equation as well. That's just for your reference. And with following this wave series to the Alton, so we do the similar things. We try to put all these wave equation can be expressed by the separation variable. We consider these 3. We consider these 3 coordination. Then we can get this one. So that means that the wave function must be single value, where it means that the n is equal to this one. And that gives start to also give our idea that we can have the quantum numbers here. So each set of a quantum number corresponding to a quantum state that electron might occupy. So in the end, we finally have the equation here to express our electron energy, which is quantized. So what does mean the quantized? Actually, you don't have to think that the quantized or quantum is a very complicated physics. Actually, what does quantized and quantum mean? It just means that your energy level can be counted as a discrete number. That's why we call it quantized 量子化，主要就是说你的能阶可以被数量级表现。So that's why we call it quantized. That's why we call the quantum number. So that means that your energy here can be calculated as a discrete value. Where we have a m here, and we have a n here. Sorry, we should use the n. So n is a constant. The n is a discrete quantum numbers here. So that's actually what we call as the quantization. Because in the beginning, if you back to the very old physics history, we always consider the wave is a continuous. You cannot count as a discrete number. But once we have a quantum mechanics, when we start to have the concept related to quantized, we found out that the wave can be considered as a particle, and the particle has a quantum, has the energy of this particle can be calculated as a discrete value, where we use electron energy expressed in here. So here just some more just extension of knowledge for your reference. That of course inside the periodic table that we can describe the result with two additional concepts. We can describe the one electron with these two additional concepts. One is electron spin, and one is this exclusion principle that there's no two electrons might occupy in the same quantum state. So therefore, we got this four basic quantum number as shown here. So for detail for this quantum number, you can look at for the textbook. But I think the main point is not like to fully understand the equation derived from the typical case to the spherical, and then in the end to get the equation that to express as shown here. It's not like the main purpose. The purpose just try to help you to understand that in the case of the very small micro worlds, that the electron movement in the crystal can be considered that the electron try to move in the case with a periodic potential. So once face a periodic potential, we divide by the four different cases. And then the most important part is that the particle can be only described as a probability. And second is that we have a concept of tunneling. So these are the two differences compared with conventional physics here. So the basic concept of quantum mechanics is to describe the behavior of electron under various potential functions. And we use this Schrödinger's wave equation from basic for describing and predicting the behavior of the electron. And then we can have the first conclusion is that we can use this one as a probability density function. And the result of applying wave equation to a bound particle is the energy of the bound particle is quantized. So this is a concept where we consider first we found out that the particle can have the standing wave property. So once you have a standing wave, you can put a wave number, and each wave number has the one particular wave function. So in that sense, we start to consider that's what we call the quantization of energy. And then also another result applying the wave equation is that the electron incident on a potential barrier there's a finite probability of the tunneling. So these are several important remarks that what we should learn from the quantum mechanics. Actually, quantum mechanics should not be considered as very complicated physics. Actually, it's a tool. Once we consider wave equation, it's actually a tool. Try to prove our speculations here. So, as I say, the main application here for sure, in the end, we are not only talk about the tunneling, but for sure this is important to help us to analyze our semiconductor device. Like I say, one of the practical case why we need the quantum mechanics is this quantum mechanics help us to understand why there is a carrier, there's an electron can flow to the top. So as I say, we apply the gate bias here. And now we all know once the gate bias is larger enough, we start to form the electrons in the channel. And we can foresee this electron can tunneling to the top, which will become the leakage current. So this is one of the example why we really need the quantum mechanics, because otherwise there's no way to understand this one. And this is going to be very useful because in the end, we will use a Venn diagram to understand this, because we will not every time to draw this device schematic. Sometimes just because nowadays this is still the very simple MOSFET, so it doesn't take too much time to draw. But if we use very complicated device, it's always very difficult to draw the schematic in a very precise way. So therefore, we will introduce in the later slide, in later part of class, which is important, that we will introduce a concept where we call as a Venn diagram. And then the Venn diagram can help us to understand the barrier, the potential barrier for each place. So for example, this is a typical Venn diagram for the one across this. If we put a color line of this one, this is this Venn diagram for this color line, where we already expressed this is a silicon. So in the case of a silicon, what we already know before, that in silicon we have the band gap. This is a band gap which is around 1.1 electron volt. And another is the dielectric. This is dielectric. So that means once we apply the positive gate bias here, so once we apply the gate bias, so you can imagine this is a cross section. From here will become the Venn diagram in this way. And once we apply the gate bias, because this is energy and voltage always has a one minor signals difference. So once you apply the gate bias, actually you try to pull down your energy. We will talk about this. So anyhow, we all know once we put the gate bias, we will formation of electrons in this region. And from the Venn diagram, that means we will formation of electrons in this region as well. And therefore, we can also expect this tunneling can be happen. And with considered tunneling, that means the carrier can tunnel through the other side. So this is the reason why we have to study the case 4, because this drawing, which is highly similar to our case 4. So that's why we have to consider that there's an infinite potential well, but then the region 1 and region 3 can be the free space, and how we understand the carriers moving towards this potential barrier here. So that's exactly the situation that we will need to understand when we analyze our semiconductor device. Okay, so this is last slide for the quantum mechanics. I hope that with this chapter that can help you to get more confidence to understand, to not be afraid of the quantum mechanics, and also start to have the link that the basic quantum mechanics, then the application of quantum mechanics in the end to our real device operation. Okay, so now we move to the next one is that we start to use some of the quantum series for our solids, which is just our semiconductor, so that we will use this quantum series. The main point here is try to understand that why there is an energy band, this kind of a concept. So first we have to understand that why there's a formation of an energy band. And we know that so what we learn from the quantum mechanics, we use a lot of the wave equation. So the wave equation is trying to understand the electron behavior. So wave equation of electron of the two atoms. Once we have the two atoms overlap, so this is one atom. But now if we have the two atoms overlap, that means that this will have the two electrons will interact with each other. And this interaction or perturbations results in the discrete quantized energy level. That's split into two discrete energy levels. I think so far you should be able to start to understand that once we talk about the energy for the one or several electrons, in the end is always showing the characteristic of the quantization. That means our energy level is discrete. So this also, in this slide, just want to illustrate this concept that once we have the two atoms moving close together, the wave function will interact with each other. In the end, we will create this discrete quantized energy level that can split into two discrete energy, as shown here. Of course, if you are very new to this field, this concept could be very abstract, a little bit vague for you, but try to, if you cannot understand right now, it's fine. Try to force yourself to accept this concept, because in the end, you found out this is pretty straightforward, but just in the beginning, you need a little bit imaginations. Okay, and also, if we start with a regular periodic arrangement of the hydrogen type atoms that initially very far apart and begin pushing the atom together, then the initial quantized energy level will split into the band. Of a discrete energy level. This is shown in this schematic. So you have, this is the distance. So once you push a bunch of, in the previous slide, we only talk about the two atoms together. But in the real crystal, you have so many atoms in the one periodic lattice. And you try to push all the lattice close as possible as you can. So you start, the lattice here will be pushed to here with another one with very close. In the end, you can start to imagine that all these crystal and atom will split into a band of the discrete energy level. Not only the one or two is actually the band. So as you see, this is a band, but this is a band, but also inside the band is discrete energy level. So you have a 1, 2, 3, 4, 5, 6, 7, 8. So that's the energy level, but it just will split as a band. So that's why we start to come out with a concept with the energy band. Also, again, that if you are new to this field, of course, it's very difficult to understand in the beginning, but try to force yourself with some imagination, because in the end, I would say that this actually is become not that important, because in the end that we will have some more important than the concept shown in here. So now, since each atom contains more than one electron, and suppose the atom in the crystal contain electron up through the n is equal to 3. So now we have this schematic. We have n equal to 1, n equal to 2, n equal to 3. So you have 3 electrons. So each electron will be surrounded by the lots of atoms nearby. So then each electron, the interaction of one electron with the other surrounding atom can be spanned by a discrete energy band. But now you have a 3, so that will become like in this way. So finally, if we consider the n equal to 3 for the valence electron, so the first 2 energy shells are completely full and tightly bound to the nucleus. And that's so if we have a 3, but and then the first 2 is a fully filled and then bonded with nucleus. But the one as a one of the interatomic distance discrete, so that means you have another atoms coming close by. That will influence the outer part. So outer part, which will be the 3s and 3p, will be interact and then overlap, because the first 2 is tightly bonded inside. So as a equilibrium distance, at the certain one equilibrium distance, the bands have again split, but now we have the 4 quantum state per atom. Are in the lower band, and also the 4 in the upper band. So the idea is here, as shown here. Original, we have a 3p and 3s. And then we consider the 3p has a 6n state, and 3s has a 2n state. But now, as the distance getting close to close, so this will split as a band, and now will become the 4n state on top, 4n state on the bottom, but only the electron will stay in the bottom, because the electron will prefer stay in the low energy position here. So that's the case where we have the electrons getting close with each other, with one reach to the equilibrium cases here. So why the 6n and 2n is actually here? So that's the SP. So we have a 6n and then 2n at here. And now we can start to read a little bit again, use the imaginations, try to redefine this region where we consider the upper part, what we call as EC, and the bottom part, where we call is EV, and then in between is our EG. So now it's getting more and more close to our the expectation drawing, because once we consider this one, once we redraw a little bit for better and simple drawing, so now we can redraw this one with EC, EV, and with a band gap in between. So that's why we start to have this what we call the band diagram. So this is the reason why we draw in this way, because in the end, just another simplified illustration once we consider the atoms getting close with each other and split as a band to the top and bottom, and the top one we call the conduction band, and the bottom one we call the valence band, and in between we call the band gap here. And also the one more thing is worth mention that now in this case the electron can only stay in here or in here, which is not be able to stay in this region because our discrete energy level stay, right? So we now have a concept of the discrete energy. Discrete energy level, that means that each electron can only stay in the E1, E2, E3, E4. You cannot stay between the E1 and E2. So this is a E1, this is E1, this is E2. So you cannot stay between the E1 and E2. So that's why in between, sometimes for simplify, we call the band gap, but actually it's called the forbidden band. The real name for this one is called the forbidden band. This one, forbidden energy band. Because due to the characteristic of the discrete energy level. But now we know that the electron can only stay inside the energy level, not outside the energy level. So inside the energy level, that means the electron can stay here, can stay here. So that's why this we call the allow energy state. We call the allow energy band, which is here. This and this is allow energy band. And if we look at the simplified band diagram as shown here, that means this is allow energy band and this is allow energy band. So these figures are actually very consistent, just drawing in a different way. But the purpose that we draw in the bottom one is because try to simplify and then more easily to draw every time. But otherwise, if we use the top one, it's very confused. For explanation, it's already confused, so we will not prefer to use a confusing thing. So the bottom one is very simple. And also, by considering the allow energy state and then forbidden energy state and the concept of quantized energy, so now we can also expect our electron can only stay here. The reason why we call the valence band is because this is the state which is full of electron. So that's why we call this valence band. So this is a place we have a full of electron, and then this is a place where we have an empty electron, because here is empty. And here is a foreign electron. And then in the end, later we will talk about this again. Then how the carrier start to flow, how the electron flow. Actually, is the electron has to, from this place, jump to the other side. Once it jump to the other side, means that it across a certain energy state and start to have the physics-based operation, which will be generate the current. So we will talk about the band diagram, the detail about this. But in this slide, just try to illustrate that the origin of the band diagram, why, how this concept of band diagram coming from, and then why in the end we have the term with forbidden band, why we have the term with allowed energy band, why we have the conduction EC and EV and EG and all these things. Okay, so what actually I would like to say is also will be redraw again. So finally, we no longer to consider this complicated drawing anymore. This only will be the one time, probably one time for your life. Then, from now on, we only consider the band diagram where we have the conduction band and valence band. If you didn't understand the previous one, that's fine, you can forget it. The purpose, the most important is this one. In between, we have a EG, and on top, we have a conduction band. And on bottom, we have a valence band. And the conduction band is empty. Why is it empty? Because the previous slide already showed this is a 0 electron. So that means everything on top of conduction band should be the empty. So now we get this, and then also we already understand in between, this should be the place that not possible to have any carrier, because we have a discrete energy state. We can only have the energy, allow energy state here, allow energy state here, not here. So that's why we call this as a forbidden energy band. And then the bottom one is a valence band. That means this is a place. In this case, we have a foreign electron. So this is a place where we have the 4 electrons. So in the case at the absolute 0 degree, electrons are in the lowest energy state. So the O state in the low band, that's what we call the valence band. Will be full, and the O state in the upper band, conduction band, will be empty. The band energy between the top of a valence band, this is top of valence band, and bottom of a conduction band, it's a width of forbidden energy band. And usually we won't mention again the forbidden energy band, this kind of term in the future. We just call the band gap. In the between, we call the band gap. That's more, first of the word is less, and then also it's more easy to pronounce. So in here we only mention forbidden energy band, but in the future we only mention the band gap, because that's more practical in once we consider the device.
Sure.
Okay, so we will take a short break here, and then we will continue later. By the way, so today you need to hang in your homework, so please put homework somewhere in the front. So, as I already said that normally we should have the 8 to 9 times homework, but I found that this is a huge loading for TA. They will take it so long to grade because we have more than 75 students here. So I decided that we only have the first homework is you need to hang in, we do the grading, and second homework I already upload is a self-practice. You can practice at home, but for sure that's still important for the exam. And third homework you need to hang in and grading, and the fourth homework will be the self-practice. So we will take turn like in this way. But that also means that if you miss one homework, delivery of one homework on time, that will cause a huge loss for your homework grading because we only have 4 to 5 homework in this semester.对，
因为我看式子，我看这两个式子好像是一样，但为什么一个要用为什么要用 exponential 去表示一个用？
因为那个是因为它会，你这是 sine wave 嘛，是因为用 sin 比较好解释。但驻波就是那个就像你绳子一样，你要上上下下。对，这样比较好去解释。对，它其实都只是为了要让我们物理上好解释，所以让你的这个数学式子表达。当然你有其他的 expression 可以表达，但是问题是那就不好解释我们的问题。对。
这个 A2的这个这个算法这边直接显示它的算法是用这个方式用这个
好问题耶。我可能要回去看一下那个课本，我忘记怎么算。
好 ，OK。那这个就是像这边老师有提到说，可以提到说这个方向，那这个地方跟方向有关吗？就是你在 region 2的这个，它是 exponential decay， 对，它应该是 decay， 可是它就有这个方向的概念吗？
还是有方向。
所以那它这边如果是负的话，代表是它的位置。
其实我再确认一下，我觉得这边还是往正的方向。
对，因为我觉得这边还是往正的方向。不然你们要把它弄过去。
对，我去确认一下哈，这个教科书上面这边写正负，我忘记了。
这个应该是负，这边是负。
对，所以这边应该是正方向，还是负方向？
负方向。
所以是负方向。
对，这个是正方向。那这个负的 K2，我在想这个是有方向性吗？因为
还是那可能它就没有方向，它只是代表一个 exponential decay， 因为它打到 barrier 里面的话，它就会一直下降，越来越长。对，那可能对原配子的话，它就没有方向性。
好 ，OK， 好，谢谢。
然后这个作业可以手写。
可以，手写可以，没问题。
没有定起
来。没有定起来的话，你要想办法把它折到就是，那不然你每页都先写名字，把它折起来。对。OK， 好，不然的话这样子到时候不见了。
This is my first class. This class visa issues.
Okay. So which department? Your ECS. Okay. So first of all, try. Yes.
I've taken this course and basically some classes as you.
Yes, and you have to.
Difficulties in that course.
No. I think you will not difficulties. Everything. My lecture is upload in the YouTube.
I've done some homework, but I've not done it on some of your page. I've done it on my.
First of all, you need to join our Facebook group, and you can be access the previous material. And every lecture I actually upload in the YouTube, so you can watch out later. And send me an email because then that means you won't hang in homework today, right? So you should hang in homework as soon as possible.
So this I've done this one.
Yes.
The quiz homework, first one.
Oh, you already done? Oh.
I've done.
Yes.
But was not known that I have to submit in this
Yeah.
way.
So then
So
just try to submit it, and then.
Can I submit sir in soft
Yes,
copy?
yes. The later the TI will come.
If
The
I
later.
make PDF.
Yeah. No. You, the later the
In the
the
later?
the end of this class, the TI will come, and then just inform them that say that I agree that you can submit
I
it.
need a day or two, sir.
Yes. So probably submit by Wednesday. Okay. Send to the contact
The other
TI.
thing is
I will
that-
introduce you to the TI.
The other thing is, sir, that I've came on scholarship and the departmental assistant has informed that maybe with some low grades the scholarship is affected. And
So you need to work hard.
basis.
Yeah, you need to study hard to make sure that this course can
Sir,
get
I'm
good
doing-
grades.
I'm doing it so hard, but I will
It's just the beginning of this class. I think it's too early.
Yes.
Yeah, you still have time.
Yeah. Sir,
to
I'm
work hard,
doing
right?
all the things, whatever I've
Yeah.
found in
Yeah.
the first of the class,
Yeah.
because I did not taken that classes
Yeah.
in classroom.
Who is your
That's why-
advisor?
Sir, Professor Danny maybe. The full name is not, I cannot
In
pronounce.
which department?
EC, sir.
What
Electronics.
What is he doing?
Professor, sir, I can write if you allow.
Danny Lian.
Sir, so shortly, he pronounced it Danny.
Okay, probably
I
you
can-
can let me know. But by the way, that you need to. Come here.还没有，怎么样？还没有到我，还没到我学学生看3个，但是应该会发好。对，大家确定。怎么样？这个事情这个题目是录的那个 test。
以上课的话，刚有上去的话，那我想问是说，那上次画出来这个图的话，那我们的那个它明明应该是说，随着gate voltage增加，对，它会有更多的电流。所以那一开始它这边存在的电流，是因为它本来有gate voltage有输电，然后有那个电流。对，老师就不是他们。
也是啊，对，你只是在没有 VG 的时候可以测它。哦，对，因为我刚想说可以测它没有任何白条，它就还是会。哦，对，哦，就对。因为它那种的几率基本上是没有的，跟 VG 上面越大的，它们是越小，对，
好，就它没有也是还是会。
对。
然后这边的话，因为这边一开始前面说，在我们这 region 的话，如果 V 小于 V 0的话，它会过去，然后会做反射。然后，那如果说，一样是1小于 V 0的话，会过一样会，就是会有几率会这样穿过去。对。
这一大一就直接整个靠，它不需要靠汤点是什么，它直接可以 overcome 就像画栅栏就直接跳这个道。对，它应该主要考虑是说，大部分情况下我们 energy 会小于这个 potential。
energy。
对，因为你 dielectric 一定很厚，它的位障很高。
V 就很大。对，
这个 V 0很大，但是你给的这个宅子的这个能量已经小于对，就是位障，对不对？所以当然如果说你今天的能量大于位障，它基本上它就跨过去了。对。
而且他们一想是。
下课再教。加下课再教。
OK， 好，那你就一起教就好，你就2个一起在中午前一起教，再下课一起教。
这样要写，因为我们是清大的，要写。
应该是，不然你先写一下好了，我怕他们改会改。Okay, so we will continue. So we actually already addressed lots of the fundamental things that you have to know, and then so later on we will start to extend a little bit what we have to know to the some question, some remaining question. The one thing I want to particularly mention here is that there's a very well known that we call the chrome penny model. So this is just a model to describe the one-dimensional periodic potential function used to a single crystal lattice. So the idea for this chrome penny model is very simple because we already illustrate that once you have the electrons movement inside a piece of semiconductor material, actually in the end we can consider the question as a electron movement in the place where we have a periodical potential difference as shown here. So this is periodical potential. So therefore, we can use this model to describe the certain characteristic here. And in this slide, we won't go very detailed, but just quickly go through the model. So this is a relation between the K, total energy, and potential barrier can be found as here. So as with previous quantum mechanical problem, the more interesting solution occur for the case where electron, the energy is smaller than our V0, which corresponding to a particle being bonded with a crystal. The electrons are contained in the potential wells, but we have the possibility of tunneling between the wells. So that's what we actually have, the conclusion from the previous quantum mechanics. And the chrome penny model is an idealized periodic potential represented a one-dimensional single crystal, but the result will illustrate many of the important features of quantum behavior of an electron, as important is in the case of the periodic lattice. So that's the main purpose for the chrome penny model. In here, we won't talk too much in detail, but this is just for your information that in the previous case, we only consider as the state function, but it's not a periodical, just a one state function. But now we can also consider as a periodic potential barrier as well. Okay, so also there's another important concept that we call the K-space diagram. So in the case of a K-space, that we can have this equation. This is one we have been shown, and can be also related to the momentum. So the parameter K is related to the particle momentum for the free electron, and also the energy can be also expressed as here. So therefore, the momentum and wave number are linearly related. So now if we do the derivative of the energy versus a K, we can have this one and also this one, and then we put the P is equal to mv, and then we got this one. And if we do again the second derivative, then we can have this equation, which we reform this equation as 1 over n star is equal to 1 over h bar square second derivative dE dk squared. So that means the curvature, because this is a second derivative, right? So the second derivative, that means we try to consider the curvature of a E versus a K diagram. So this is E versus a K diagram near the minima of the conduction band energy. This is a minima of the conduction band energy is related to the effective mass of electron. So that means this is effective mass. So that's also the some additional small concept related to the K-space diagram. So we can consider the EK diagram and then to derive the effective mass. Okay, so now we move back to the discussion related to the energy band, because we already know that what would be the energy band look like, but now we also will want to understand that whether we are able to use the energy band to understand the electrical conduction, because in the end, as being the electrical engineer or engineer, we try to simplify, and also one side we want to simplify the question. On the other side, we want to generalize our tool, because we want to have one tool that be able to use for the so many different aspects. So the tool we have now is a band diagram. So we are consider that whether we can also use the band diagram to understand the electrical conduction or not. So as we know how the electron movement, the carrier movement in the solid is that you have the one electron will move to the other empty space. That causes current, that causes electron conductions. And whether this behavior can be also described by the band diagram. And the answer is for sure yes. We can consider the band diagram as we show in here, where we have a EC, EV, we have the EG. And now we all know what we have been understand the basic origin of the valence bands, conduction band. So we already understood that in the bottom of the valence band is a place full of electron, and then in top of the conduction band is a place where have an empty energy state. So we have an energy state, discrete energy state here, but it's empty. We have an energy state here, but the energy state is full of electron. So in the end, if the electron can certainly across to the forbidden band, that's a band gap, to across the forbidden band and reach to the other side, and this will cause the current flow. So this is exactly can be used to describe how the electrical conduction in the solids here. So now we start to generalize our tool, not only to understand how the energy level inside the solid, but we can also use this one to understand the current conduction in the solids. So as I say, the energy state in the valence band are completely full, and the state in the conduction band are empty. So this is already described here. So we can consider this small region where is our EC and EV as well. So this is EC and this is EV. And now the purpose, what we need for the conduction is that the electron need to across from the bottom to the top, in the end become the current. So this can cause the current. So for T is larger than 0K, some electrons have gained enough energy to jump to the conduction band, and therefore there's some empty in the valence band. But in anyhow, this is a case to describe how the electron conductions happen in the solids here. But now we also start to understand that the EG, the band gap, is crucial, because if we want to have the conduction, then the electron need to jump over this EG and reach to the other side and become the current. So that means if we have the two materials has a different band gap. So this is a EG1. This is EG2 here. And for example, the EG1 can be silicon, and the EG pool can be any materials that are larger than the band gap is larger than silicon. For example, let's say the diamond. So we all know the condition where you have the electrons, condition where you have the current electron mass to across and reach the valence band, reach the conduction band, and become the current. So that's what we call the I1. Or the same, the electron in the buttons reach the conduction band and become the current of I2. So without knowing any material property and any very complicated physics, from this illustration we can already know the EG2 is larger than EG1. But this also means the electrons need to overcome such big band gap and to reach to the other side. Definitely is much more difficult. The probability is much lower. So we can expect the current of I2 must be smaller than I1, right? I think that's the reason why the band diagram is powerful. So far, we don't involve any very complicated equation derived, just a schematic drawing. But now we can already understand. Ideally, the current in the second semiconductor, where it has large band gap, should be smaller than the current in the first semiconductor, which has a smaller band gap. And also, if you look at the material size, we all know the diamond, for example, should be very close to the insulator because it's one of the hardest material in the world, so should not be very conductive. So we can also expect the diamond has a very low current. So in the end, I hope that with this explanation can get correlation with your daily life experience, that even with band gap that already can explain the conduction property in the many material, no matter for semiconductor, even sometimes for insulator, we can also use a band gap to understand. So that's the purpose why we need to again to illustrate the band diagrams concept. So in regarding to the K-space diagram, there's also a small additional concepts related to the rack band gap. So if you look at the bottom one, the top one, and then the bottom one, we found out that the top of the conduction band is in the same position of the bottom of a valence band. So that means this is the electron jump from the bottom to the left only need to overcome certain energy. So this material is that we call the direct band gap. But on the other hand, there's some material that your top of your valence band is not aligned with your bottom of your conduction band. So that means if you want to have the current, the carrier first need to jump to a certain energy, but also need to have a certain momentum to reach to the other side. And you can find out that it must be very difficult because you need to have to reach the two criteria. One is energy, second with the momentum, and this is how we call as an indirect band gap. So there's a very famous, well-known material that has been used for our life. That's because of due to the nature of the direct bandgap property, which is a gallium nitride LED. The reason why the gallium nitride material is so suitable for light emission because of it's a direct bandgap material, so the efficient to transform from the energy to the light is very high because you only need to cross this energy. And the problem for the indirect bandgap is you need to involve not only the energy but also the momentum, so which is difficult to emit the light. For example, the silicon material. So silicon material is one of the most famous materials that shows the indirect bandgap. So that's why you never heard about people use a silicon as a light emitting device. So since we start to talk about the conduction, so that means we start to need to move step by step, slowly to move to the next question we are interested in is that how to derive the current, how to have the understand the current flow in the semiconductor material, and how to understand the concentration of the electrons and holes in the one material. So far we didn't talk about this, we just talk about there's a one single particle flow, and then we talk about how could possible to tunneling, and in the end how to become the current. But then now we start to move to the next level that we want to understand the current. So the first current we would very often to talk about is the drift current. So basically the current, which is just the net flow of the charge. So if you consider this is a typical current equation, and then we will talk about more current equation later. This is just for your basic understanding. If there's a force applied to the particle, and particle can move, that means this particle gains some energy. If external force is applied to electron in the conduction band, they are empty energy state which electron can move. So if you have the force applied, and then if there's an empty state in the conduction, then you can start to push the electron moving into the empty state, and in the end become the current. So this is one of the schematics that when there's external force is applied. So once you have the external force applied, you actually destroy the equilibrium case. You certainly will influence the distribution, and also certainly will influence the empty state here. So therefore, usually you will get this asymmetric distribution. So you have this asymmetric distribution in the EK diagram due to an external force is applied. But we will talk about later that how actually the current can be calculated. This is just a little bit appetizer for everyone that start to get a sense that how the current can have. But in the later we will talk more detail. But before we talk to the current, we have to consider another pretty important concept that we call the density of states. This density state, sometimes we just call as a DOS. When I was first time to learn the semiconductor physics, I think it's always pop out with some very, for non-native speaker, English speaker, it's always difficult to understand what does mean the state, because state is another the typical words that will occur in our the typical daily life, especially if you talk to the Mandarin. But now you can get the state is when we talk about state, it's mainly related to energy state, it means that you have a certain discrete energy level that can or cannot have the electron. It depends on its as an empty state or occupied state. So in anyhow, it's just like this is let's say if you have the band diagram EC and EV. So now we know, of course, in the forbidden band, inside the band gap, there's no energy state because ideally we cannot have. But we all know there's a state here. So these are the empty energy state. And in the bottom of valence band, we still have the energy state as well, but just each state is already occupied by electrons. So we have the full energy, we should say occupied. So this is the moment when we first to discuss about state. So state, just like you can imagine, is an empty seat. At each in the classroom, we have empty seat here. It's an empty state. We have a seat that has somebody sit in. That's an occupied state. So that's what we call the state. But to be honest, state, if you look at some Mandarin translated semiconductor book, it's very difficult to understand. I think in the moment they say they translate as a 状态 or type. They use a type. It's very difficult to understand. But I hope right now you get more sense about the state. But another term is the density. We also didn't. Density, of course, is a term that we should learn from the high school physics, chemistry. We talk about lots of density. But the point why we mention density in the semiconductor, I think the first time we talk about the density is when we mention about there's a thing called probability density function. This is a moment we mention the density in the first time in this class. Of course, if we look at the crystal structure, we also calculate the density of how many atoms in the one volume. But if we consider the carrier, we actually mention a key term called the probability density function. So now the purpose is that from the name of the density state is already implied. We try to combine the probability density function with the energy state that can help to do something. So this is just what I want to illustrate. Why there's a term density of state coming here? Because the density state, of course, you look at as I say, most of the students in this classroom are non-native English speakers. So for sure, when the first time we look at about the density state, this kind of term is always get very confused. Even you look at the Mandarin translation, I think they say that the 密度态, something like this. But they still also get very confused. But the idea of the density state is that we want to have a function to combine the probability density function with considering the electrons inside the energy state. So that's the purpose. So since current is due to the flow of the charge, the important state in the process is try to determine actually the number of the electron and holes. Because if we want to understand the current, first we need to how to estimate how many charge can have, right? So we need to have the way to determine the charge, to determine the number of charge, to determine the number of electrons and holes that will be available for conduction, because that's crucial, because the current is just mainly due to the flow of the charge. So the next question becomes, how do we know how many charge being available? So how do we determine the number of the electron that being available that can use for the conduction? So that's our question. So the number of carriers that can contribute to the conduction process is a function of a number of available energy. Or quantum state. So now it's back to the question. We want to know how many electrons here. We want to know how many electrons here. But the question will be, how many available state there? If you only have a 3 state, for example, like in this classroom, if you only have a 3 seats, for sure the maximum the people can be in this classroom will be the 3. As usual, if we only have a 3 state, then we can only have a 3 electron. So the question is evolved into the next level is that to determine how many electron and holes, then first we need to understand how many quantum state, how many energy state is being available. So that's actually our question. So because of the number of carriers that can contribute to conduction process is mainly determined by available energy of a quantum state, which is described here. So we must determine the density of these allowed energy state as a function of energy. As a function of energy in order to calculate electron and hole concentration. So our goal is calculate the electron and hole concentration. But before we calculate, first we need to understand density of these allowed energy state in as a function of energy. And where is the density of allowed energy state? This is the density of allowed energy state. We need to understand how many allowed energy state in here. So that's why this density of allowed energy state become the density of states. In a short way to describe here is what we call the density of states. So that's why the question back to as a title, how do we estimate, how do we have the density of state function? This calculation sometimes is not very straightforward, but if you try to calm down and think once, in the end you should be able to find out that it's actually pretty much makes sense. Okay, so now let's look at how do we estimate the density state function. Again, so if you look at in here, we won't do the very detailed derive for the equation because it takes too much time. The purpose for this class is not the mathematics, physics behind. So the first of all, the density of a quantum state is a function of energy E, so can be expressed by here. And as the energy of these free electrons becomes small, now the number of available quantum states decrease. So then can be expressed by here. So therefore, the density of allowed electron energy state in the conduction band is described by this equation with a function of E minus EC. And the density of allowed energy state in the valence band can be expressed by this function with this GV with a function of EV minus E. In this equation, it's very difficult to understand, but of course, we try to have some schematic to help everyone, also to more visualize the ideas behind. And what we're going to use is a band diagram. So, with considering the band diagram, we all know this is EC and EV. And this is our energy. But now we try to have the equation to estimate the number of the available quantum state in the conduction band or in the valence band, which is this one. This is a GCE. This is a allowed energy state in the conduction band. And this is GVE. This is allowed energy state in the valence band. So that's the function of this one can become like here. Because when E is equal to EC, this will become 0, right? When E become EV, this will become 0. So this is 0. So this axis is GE. The derive for this equation is not that important, but to understand this equation is more important. Okay, so the next one, now we have the density state function inside conduction band, inside the valence band. But again, because we try to deal with a large number of particles, so we are interested only in the statistical behavior. We are interested in the statistical behavior of the group as a whole rather than each individual particle, because we are trying to dealing with a huge amount of particles. It's not possible to determine the behavior for each one. So we want to understand the behavior of all. So that's why we need to apply the certain statistic laws here. And there are the three main statistic functions that we very often use to deal with different kind of the particle or carriers. The first one is a Maxwell-Boltzmann probability function, which can be written as Fe is equal to exponential E minus EF over KT. So this is considered for the Maxwell-Boltzmann probability function. Is considered the particle are considered to be distinguishable by being number, but with low limit of a number of a particle allowed in each energy state. So that means that this is considered there's a particle can be stay in the one state, but the problem is that there's no limit for each state. So that means this state can contain as many as a particle, but there's only one specific case for this one is a gas molecular. Because consider gas, you can have as many as a gas, like in this room. You can have as many as a gas molecular in this room. So that's why the Maxwell-Boltzmann Maxwell-Boltzmann can be only used, consider the gas molecule. But the second one is more related to our case, is how we call the Fermi-Dirac probability function. So in the case of Fermi-Dirac, it can be written as here. One over 1 plus exponential E minus EF over KT. So this again, this is considered the particle are indistinguishable, but now only one particle is allowed in the each quantum state, so which is exactly fitted for our case. So this can be used to consider the electrons in a crystal, which is important for our semiconductor device and physics. Of course, there's a third one, it's called the Bose-Einstein function, which is this one. Fe is equal to 1 exponential E minus KT minus 1. So the particles are indistinguishable, and there's no limit the number of particles per me in the quantum state, but this is particularly useful for the photons. So there are the three general statistics law, and then we will only use the second one, which is a Fermi-Dirac probability function, because that's very suitable for the physics based on the electrons. So now we start to move. So since in here we mainly talk about the Fermi-Dirac probability function, then we have several terms need to talk here. The first one is the number of density capital NE, which is a number of a particle per unit volume per unit energy. The function GE is a number of quantum state per unit volume per unit energy here. So if you consider Fermi-Dirac distribution, actually it's a capital NE over small GE here. So the capital NE, that means number of particles. And then the G is number of quantum state. So I think the probability just depends on the how many particle over how many O, right? How many O particle, but how many O particle is equal to the how many available quantum state, because if the base cases will be the O quantum state filled with one particle, so that's a total number. So the top one is the number of particle, and then the bottom one is the number of O particle, which is equal to the number of quantum state, can be considered as a Fermi-Dirac probability function. And there's a term of the EF here. So the EF is called the Fermi energy. So the energy EF is called the Fermi energy here. Since it's probably your first time to heard about the Fermi-Dirac probability function, so let's just spend some time to talk about this function. So the Fermi-Dirac probability function, we can consider the several extreme cases that get some better understanding. But so first one is if we consider T is equal to 0K, and we consider the case when energy is smaller than EF, which will be, this is EF. So this is the region where energy is smaller than EF. So if exponential E minus EF, since E is smaller than EF, then this will be approach to the exponential minus infinite, which will be equal to 0. And then this becomes 0. So then, in this case, the probability here will be equal to 1, which means the probability when the energy is smaller than Fermi energy is all equal to 1. In the case of a t equal to 0 k here. And second case is if you consider E is larger than EF, and then as usual, this can be approximate as here, and this will approach to the infinite. And we consider this one, then this will be equal to 0, where means this region becomes 0. And also in between, when E is equal to EF, we get this 1/2. So that means here. So that means the function is look like in here. So this just try to help you to get sense about this probability density function. That means that in this case, when energy is smaller than Fermi energy, the probability is 100%. When the energy is larger than EF, the probability is 0%. And when E is equal to EF, that's equal to half, 0.5. So that's so calculation for the Fermi-Dirac probability function is very simple. So now we start to get him a little bit further state, because we want to combine these two together. So if we assume that the system contains 13 electrons, so if we have the 13 electrons here, assuming here we have the discrete energy state 1, 2, 3, 4, 5 here, and then these all fill. These all empty. So that means the Fermi energy is likely in here. So the electrons are in the lowest energy possible energies, the lowest possible energy state, so that all states below EF are filled. And all states above the EF are empty. So now we can try to, again, to use this plot to understand this case. This plot where we already draw before, this is a GE, that's our allowed energy state versus energy here. So this plot actually describes that this is EF. When below EF, every state are filled, which means here. And when beyond the EF, these all are empty. So this is also, we can use this graph where we described before to understand this phenomena as well. So the GE here means available energy state. But now, in previous case, we consider T is equal to 0K, which is an extremely ideal case because in the reality system, definitely T is always larger than 0K. But once the T is larger than 0K, that means the electron gains a certain amount of thermal energy. So the some electrons can jump to the high energy level, and that means the electrons are among the available energy state will change. So this means that this is our EF. Due to some of the thermal, electron can stop to jump because of the electron will gain some energy. And this will also certainly change our Fermi-Dirac probability function, which we have shown the F, E, and E. And in the case of T equal to 0K, the distribution function is shown as we draw before. But now, once the temperature increases, the distribution function will start to change. Will be something like this one, where we have the T2, T1, and then T2 is larger than T1, larger than T0. So that means, so this is considering the temperature increase. So the probability of energy above EF being occupied increase. As the temperature increase. So this is sorry. So in original, this is EF. So that means this is below EF is all filled. This is above EF is all empty. But with temperature increase, some electron can be jumped across to the top. So therefore, some of the electron can be occupied. And you will see here it's no longer as a 0. Your probability in the empty region is increased. So I think that quite makes sense, right? Because you get some energy to excite your electron, so electron can start to join, and then we can expect the probability here is no longer 0 anymore, and this can be also be improved with this function. So the probability of energy above EF being occupied increase as the temperature increase. So that's the main key point here. Okay, so finally, we can do some simplification, if we consider the case when E is minus EF is much smaller than KT, and there's a approximation that we call the Maxwell-Boltzmann approximation, and in this case, this equation can be transformed as this one. Exponential so that's just a mathematical approximation, and in this case this is original distribution, but now with Maxwell-Boltzmann this equation will be approximate like in this way, but we will be only valid when E minus EF larger than KT. So this is just a mathematical trick, it's nothing special. But the most important is that you need to understand the concept of the energy state, allow energy state, and then because we cannot determine the one individual carrier, we are more interested in the carrier as a whole group. So that's why we start to introduce the probability function, and then the most important one is the Fermi-Dirac probability function. So finally, this is what we discussed in this chapter. The discrete allowed electrons energy state in the end can split into a band. That's we call a band diagram. Once we have a bunch of crystal being, bunch of atom being very closely with each other, and therefore there's a concept of allowed and forbidden energy band. And also we introduce some additional concept in the EK diagram, and the purpose is to understand the difference between the indirect and then the direct band gap semiconductor. And the last one is most important one, because this should be the one usually you don't hear this from other place, but this is very important for later calculation and estimation. So in dealing with a large number of electron holes, we must consider the statistical behavior of this particle. And in here we mainly use the Fermi-Dirac probability function, and which gives the probability of a quantum state in the M and in energy E being occupied by one electron. And there's also the concept what we call the Fermi energy was defined. Okay, so in this chapter we still mainly try to extend a little bit about the knowledge where we have the quantum mechanics to use this quantum theory to our solid, and in the end we have the concept about the band diagram. And the next goal is that we want to understand the current. But if you want to understand the current, first we need to know how to estimate the carrier. We need to how to know to determine the electron in hole. So that's why we first the question has to be addressed will be that how to determine the electron in hole. We introduce the concept of the density state, which is to describe the allowed energy, quantum energy state in a certain place. And also we need to apply the statistical law, especially the Fermi-Dirac equation, to try to understand the whole particle behavior as a whole rather than the single one. Okay, so I think we will stop here, because of the next chapter will be just try to combine what we know, the Fermi-Dirac function, the allowed energy state. We try to product multiply by these two, and then we get some result for the electron in hole concentration. Okay, so we will stop here and then see you all next week. And also remember to deliver your homework right now.